Okay, everyone, welcome to another week of the Experimental Math Seminar. This week we have Orli Herscovici, who's going to talk to us about the unification of set partitions.
Thank you for invitation. Great to be here again. Correct pronunciation of last name. Great job. So I will talk about unification of set partitions. And before we'll talk about set partitions, I would like to start from how it started. It started not from set partitions, started from something more general. We started from two-shot polynomials. And actually, our purpose was to consider some generalization of two-shot polynomials. But before we will go for generalization and what we got from this generalization, I will start from some facts about two-shot polynomials. So first of all, two-shot polynomials can be defined as n polynomials in a few different ways. For example, we can define it via generating function. Here we have two exponential functions, e to x times e to t minus 1. We can define it by recurrence relation. For example, here we can see one of recurrence relations which contains the polynomial itself and the derivative of the polynomial. We can define it from another recurrence relation here of binomial type, for example. And of course, we can write it explicitly. And in an explicit form, two-shot polynomials have Stirling numbers of a second kind as their coefficients. And as we know from all courses from undergraduate, Stirling numbers of a second kind have this nice recurrence relation. And this recurrence relation is definitely have a combinatorial nature. They're mostly related to set partitions. So now about generalization. So there are combinatorial people working on generalization of polynomials or numbers or whatever usually use Q calculus. So if you don't work with Q calculus, so let me define a few terms from Q calculus just so that we will know about what it's talking about. So it started in 1910, and Jackson defined difference operator, dq of f, which is ratio of fq of qx minus f of x to qx minus x. Obviously, from this definition, the parameter q should be different from 1. Today, we call it Jackson derivative usually. Now we can also define a few other things closely associated with this derivative. First of all, we can talk about a q integer. So q integer n is defined as ratio q to power n minus 1 to q minus 1. And if it's integer, it has nice representation as sum of powers of q. But actually, q number can be any number. It can be real, it can be complex number, but for q integer is just more combinatorics behind it. And if we consider application of this difference operator to the power of x to n, we just get here coefficient q integer n times n minus 1 power of x. Of course, we can easily see that if q approaches 1, the Jackson derivative just approaches the Newton derivative, and our q integer n will be just a regular integer n. So as in classical case for Newton derivative, we have exponential function to be an eigenfunction of the differential operator. So here they have also such function. This will be q exponent, and there are different forms to write q exponent. I will present just this one as a power series. So we have a form very similar to Taylor series of exponential function. We have here powers of x, and now just instead of n factorial, we have a factorial of q integers. So we have actually here a few things. We have here differential operator. We have here exponential function. So if we have numbers and factorials, so if we will consider, for example, again, the definitions of two-short polynomials, we can take any of them and starting from this point to build a consistent theory for such generalization. For example, we have here exponential functions, we have derivative binomials, we have another relation for Stirling numbers, their recurrence relation. So we can start at any point by using Q calculus that we just saw its definition. So let's consider the form of two-short polynomial. So as I said, we have Stirling numbers of a second kind as coefficients of two-short polynomials. Again, it satisfies this recurrence relation, but Stirling numbers of a second kind appears also an expansion of nth power of x in terms of following factorials. So in works from 1933 and 1948, Karlitz took this relation as basic relation for his generalization. So instead of power of n, he considered power of q number x. And instead of the following factorial, he took its q analog. Another addition here, coefficient q to power of 1/2 times kk minus 1. And then the rest will be the q analog of Stirling number of a second kind. With such definition, Stirling numbers, their q analog satisfied these recurrence relations. So we can consider it with the classical form, Stirling numbers just replaced by their q analog, and the coefficient k, the integer coefficient, is replaced by q integer k. Later in 1978, Mill also defined an analog of q of Stirling numbers. He also took the same recurrence relation, actually the same trick, the nth power of the q number. Also here, q following factorial. And then just without any q, he defined the coefficient here to be a q analog of Stirling numbers. But such definition we should pay somewhere. So the payment comes in the recurrence relation for Stirling numbers. Now, the recurrence relation, again, we have here q Stirling numbers. We have here q integer k, but here there is another coefficient, q to power k minus 1. And comparing those two analogs of Stirling numbers, we understand that they're actually pretty the same. They are different by a factor from one from another. However, this form defined by Karlitz is more natural if we consider combinatorial statistics. Statistics on
did Mill know about Karlitz's work, or was it a rediscovery?
No, I believe he knew.
Ah, thank you.
However, there is 30 years and Karlitz was pretty famous, so I believe his works were, yeah, because the work of Gould from 60s, so I believe he knew about this work.
But they only differ by power of q, right?
Yeah, by power of q, exactly.
Thank you.
So the main difference is in a recurrence relation. So if you consider it applying to some statistics, we somehow need to explain this factor for combinatorial statistics. Well, here we have just to consider something more clean combinatorially. So these numbers have different combinatorial interpretations. Different statistics were defined for these Stirling numbers. But the question is, again, if we consider, if we are going back for all definitions, so we are talking about enumerative combinatorics, so we would like to get different aspects. We would like to get an explicit form, and we would like to get the recurrence relations and the novel combinatorial interpretations, and we would like to get also a generating function. So, but the problem is here in generating function. So we have Q-Stirling numbers. If we just going back and define something like this for two-sharp polynomials, it still has no closed form for generating function. There are other generalizations which defines some generating functions, but all those generating functions appear as infinite series. Infinite power or other series, not something closed explicit expression. So we would like to consider something, again, we were still thinking about a generalization of two-sharp polynomials, so we took something else. And the definition came from the so-called non-extensive statistical mechanics. So in 1988, based on experimental data, Salles defined the deformed exponential function EQ of x. And he defined it as 1 + 1 minus q of x to power 1 over 1 minus q. Again, from this definition, we can see that parameter q should be different from 1. And the nice property, the nice thing that happened around this function, that this function led to developing Q algebra as it appears in work of Borges, for example, from '98. But we would call it a Q calculus, another Q calculus associated with this exponential function. Again, if we are talking about calculus, we have here deformed exponential function, which will be an eigenfunction for another differential operator, which will have this form now, 1 + 1 minus q times x. And here the derivative will be already the, again, Newton derivative. As q approaches 1, our deformed exponential function becomes classical exponent. And here it's worth mentioning that in work of Karlitz from 1956, he already considered function of form 1 + lambda x to power mu, where lambda and mu are related each to other, but the same relation. The product should be equal 1, like here. But function of Karlitz did not get further development. It's used mostly for generating some degenerate forms of polynomials or numbers, but it's less considered for combinatorial applications. And so to define our generalization of two-sharp polynomials, so let's consider we started from generating function. So we need exponential function, we have it. We take deformed exponential function. We have a generating function for two-sharp polynomials, which contains two exponential functions. So we replace each one of them by a deformed exponential function, but we take different parameters. P for an external exponential and Q for internal exponential function. So now our generalization of two-sharp polynomials will depend on two parameters, P and Q. And as classical two-sharp polynomials have Stirling numbers as their coefficients, we called the coefficients of our PQ two-sharp polynomials as PQ and K. Again, this is the classical recurrence relation for Stirling numbers. And in a joint work with Tawfiq Mansour in 2017, we proved that the coefficients SP, Q, and K satisfy the following recurrence relation. So here we can see, as we said, for exponential function itself, parameters never takes value 1. But then we are going just as limit as limit. But here, when we are already speaking about, for example, recurrence relation or all other terms, we already can use values of P and Q, again, as limiting, but here we can see it. If we will take P equals 1 and Q equals 1, we will just obtain classical recurrence relation, this one. But the problem with this recurrence relation is that it has non-combinatorial form. And it's not suitable for enumeration because these two signs, minus here and minus here, prevents from this recurrence relation to be properly combinatorial. But still, originally, Stirling numbers had combinatorial interpretations.
But these polynomials have positive coefficients, obviously.
In what variable?
Right?
In variable P and Q?
Yeah, the polynomials for any n and q and k, it's a polynomial in P and Q. So it's positive coefficients. So it's potentially.
No, because you have minus.
Okay.
Minus
no, the
here.
recurrence has minus, but it's possible that sometimes it still has positive coefficients, but I guess it don't.
Yeah.
Yeah, okay, thank you. Thank you.
I actually don't remember their coefficients. I actually don't remember are they positive or not.
But you don't know whether they have a combinatorial meaning as some statistics.
Yeah, but yeah, of course, we have different other rules. But if you are just consider like enumeration as always adding something and to our statistics, those minuses are just not looking good for explanation. So how to explain them?
Yeah.
Okay, so again, but these have combinatorial interpretation. So we believe that something combinatorial can be considered here. So let's go for combinatorics. So if we will take a set of n integer numbers, we consider partition into k non-empty disjoint blocks. This is just standard notation. And let's consider some example. Let's take this partition. Why do I call it standard? Because if we consider, usually when we talk about set partition, we say unordered set partition. It's case that the blocks and the elements inside of blocks are unordered. So just as standard form for writing those partitions, we write them in increasing number of elements inside of blocks, and the blocks themselves we write in increasing order of minimal elements of each block. So if we have such notation, what happens if we will write it in non-standard form? So let's consider some. We can see here that this is very similar to the previous one, just we have some mix here. And now let's consider how hard should we work to make it standard. And to make it standard, we need to write everything in increasing order. So for example, for blocks, we need to put this one to shift it to the right. We need to take this one and to shift it to the right. So we need a movement of 2 blocks. So it will be written as u squared. And now for elements, we need to shift this one to the right, this one to the right, and this element to the right. 3 elements, so it will be written as d cube. We define function as nkuv, which is a generating function we are counting over all set partitions with respect to two statistics. Statistic NSB, non-standard block, how many blocks we should move to the right just to make it standard, and non-standard element, how many elements we should move to the right to make it standard. And in the same way, work with Mansour from 2017, we proved that such functions satisfy these recurrence relations. So everything is enumerated. And if we will consider here the coefficients, and we'll go back just a little bit for previous function SPQ, we can see that these functions are very closely related. They have the same initial conditions. So the function, the coefficients SPQ and K is just the values of our SNK UV. Then we take U equal to P minus 1 and V equal to Q minus 1. So our coefficients do have combinatorial interpretation. And this was very nice because the generating function, the deformed exponential function, came from definition of, from considering of entropy, which I'm sorry if it's very rude, but it's can be considered as measure of mass. And actually we applied for ordering set partitions, for ordering to bring it in to the standard notation. So we order our mass in partitions. Now the question is, what will be explicit expression for this function SNKUV? And in 2019, we showed that the coefficient of at u to power I, v to power j, which means we have exactly I blocks to shift to the right and exactly j elements to shift to the right. And this coefficient will be given by product of three Stirling numbers. Two unsigned Stirling numbers of the first kind and Stirling number of the second kind. So now our PQ2 short polynomials can be written in explicit form. So this is their form, and we can see that for any integer coefficients, if we will take parameters p q to be integer, the coefficient will be integer. So some special cases for these polynomials, and we will use here notation of Moskin from 1971, they correspond to following cases. When we consider sets of sets, so our blocks and our elements are unordered, the order does not matter. If we consider the coefficients, the analog of the coefficients S and K, this will be exactly Stirling numbers of a second kind. This is the sequence in sequence number in Online Encyclopedia of Integer Sequences. This case corresponds to P equal 1, Q equal 1. If we order elements inside of blocks, but blocks themselves are unordered, we have the following generating function, and our parameters will be P equal 1, Q equal 2. If our blocks are ordered, but elements are unordered, we have this generating function, parameters P equal 2, Q equal 1. Finally, lists of lists, order of blocks and order of elements inside of blocks do matter. So we have this generating function, and this case corresponds to P equals 2, Q equals 2. So we actually covered 4 kinds of set partitions by this one generating function with 2 parameters and 2 statistics. But when I talk about the results with Alan Sokol, he said, okay, nice, but what happens if the partitions are cyclically ordered? And cyclically ordered blocks can be cyclically ordered, or elements can be cyclically ordered, or both of them. So what happens then? Can we generalize it in such a way that the generating function will cover all 9 kinds of set partitions? So before we will consider generalization of set partitions, let's consider generating functions describing those cases. So if our elements are ordered, cyclically ordered, we have 3 different cases. Either blocks can be unordered, then we have the generating function with 1 log and 1 exponent, order blocks in 1 log function, and finally cyclically ordered blocks. Here we will get 2 logarithmic functions in a generating function. If the blocks are ordered but elements are unordered, we have this function, and for ordered elements, we have another functions containing log. So if we consider these 5 generating functions, 4 of them have logarithmic function inside of them. So we are going back to Q calculus. So this is our generating function, our deformed exponential function, with Q different from 1. But since we are going to consider combinatorics, let me rewrite this function in more combinatorial way. So I will write it with parameter beta. Here, 1 minus beta t to negative power of 1 over beta. Now parameter beta should be different from 0. And in the works of Thales and Borges, there appear a deformed logarithmic function, which is again compositional inverse to deformed exponential function. So in our annotation, deformed logarithmic function will be t to negative beta minus 1 over negative beta. But actually, if we consider generating functions that we have for set partitions, we are interested not in logarithmic function, but we are interested in negative log of 1 minus t. So negative log of 1 minus t in its deformed version will have form 1 minus t to negative beta minus 1 over negative beta. Now, comparing these expression with the definition of deformed exponential function, we actually can rewrite our logarithmic function in terms of deformed exponential function. We have difference between 2 functions. So if for exponential function t equals 0 gives us that the e beta will be equal 1. Here, if t equals 0, we will get that such a logarithm will be equal 0. And we need to take into consideration this difference between 2 functions. So this is our function, just following definition of negative logarithm relevant for us. We consider function e. Now the parameter will be a ratio of 2 parameters beta and alpha, and a variable alpha t. So this is our function. And we will demand that our parameters alpha beta for such function will not be equal 0 simultaneously. So if one of them is 0, the second one should be different from 0. And again, equality to 0 is as a limit of variable. So based on this function, we define function f, depending on 2 variables x and t and 4 parameters, alpha, beta, lambda, mu. This is our function. So we have here two deformed exponential function. On one hand side, we can see here that this reminds the form of generating function for PQ to short polynomials. On another hand, it takes into consideration logarithmic function, but here we have another term containing Kronecker delta function. And this is our compensation to difference between two functions, deformed exponential and deformed logarithmic function. So this term will be equal 1 only in case if alpha equals 1. Otherwise, it's just 0. So if we will take this function, this function will be built just for shortness. The quartet of these parameters we will denote by v bar. And so this generating function f will be generating function for some other functions, un, depending on variable x and for parameters. But actually, so we show that these functions un, they are actually polynomials for any n starting from n equal 1. It will be polynomials in variable x and parameters alpha, beta, lambda, mu. So here we can see this is u0. And here we have, we can see our compensation, but then from index 1, we already get polynomials, and we can see here symmetry between pairs of parameters, alpha, beta, and lambda, mu. So regarding consistent theory, so we saw that two short polynomials, for example, can be defined through the recurrence relation containing polynomial and its derivative. So recently we proved that, for example, polynomials un satisfy the following recurrence relation. So we can see here the entrance of polynomial itself and its Newton derivative with respect to variable x. As initial condition, we take the first regular polynomial that we saw, u1, which is equal x. Now the coefficients of such generalizations. Again, two short polynomials have Stirling numbers of the second kind. We define our coefficients as SNK with parameters in V bar, and we proved that these coefficients satisfy the following recurrence relation. So if we consider it as the analog of Stirling numbers, which have triangular form. So here we have two sides of our triangle, and this is the internal part. And the internal part does remind the recurrence relation for Stirling numbers of the second kind. For a certain number of parameters, we will get exactly the classical recurrence relation. So now let's consider again the combinatorics behind these numbers, behind these coefficients. So we already saw two statistics, NSB and NSE, non-standard block, non-standard element, what we enumerating in for PQ to sharp polynomials. But now let's step away from partitions, and we'll talk a little bit about permutations. So if we'll take permutation sigma 1 up to sigma n, the element sigma j of this permutation is called right to left minimum if it's if sigma j is less than all elements on the right from it. And we in 2019 proved the following: if we will consider the set of all right to left minimum of permutation. And we will consider set of non-standard elements of permutation defined in the same way as we defined it before. Then we have, first of all, that two of these sets are disjoint sets. And if we will consider their cardinalities, the sum of their cardinalities will always give us n. So they are just, the statistic NSE is just complementary to statistic right to left minimum on permutations. Okay, so now we are ready for set partitions. So if we will consider set partitions in such form, so double index relate to the enumeration of elements inside of blocks, and the single index is just for block itself. So BM will be a minimal element of M block or opener of M block. Our statistic NSB here just formal writing what we already were talking about, statistic NSE, and we define here two new statistics. We define statistic right to left block and right to left element. Very similar to statistic right to left minimum, but if you consider permutation, you will agree that element 1 will, the minimal element of permutation will be always a right to left minimum. So we will not consider it in statistic RLB. So we will count all blocks in a sequence of openers, like in statistic R right to left minimum, but we demand that this opener will be greater than 1. And a similar way for the elements inside of blocks. So again, we will enumerate all minimum elements from the right to the left on condition that these elements are different from the minimal element of the same block. And now we define function as bar, depending on indices nk and parameters of alpha, beta, lambda, mu. Here we enumerate our statistics RLB, NSB, RLE, and NSE. And now let's consider what happens then. So if we arrange our elements of set n into k blocks, let's assume that we already arranged n-1 elements, first n-1 elements. It can be done into k-1 or into k blocks. So if elements are already ordered, arranged into k-1 block, we have to add our element n as a separate block. So if we will insert is a last block of our partition, it will increase statistic RLB. So here our coefficient alpha. Otherwise, we will increase statistic NSB, and we have k-1 opportunity to do it. If our n-1 elements are already ordered into k blocks, we need to insert n into one of the existing blocks. So if it will be inserted as last element of block, we will increase statistic RLE, and we have k opportunities to do it. Otherwise, the statistic NSE will be increased, and we have n-1 opportunities to do it. So summing up all our chances, we get this recurrence relation. And here we also can see how statistics RLB NSB and RLA NSE are complementary to each other. And this is exactly our recurrence relation that we got before. But how we apply it to cyclically ordered partitions? So if we have cyclically ordered partitions, we consider it like one of the blocks, or like we have a chain that can be opened in some place. So it can be opened in 4 different ways. So for example, such cyclic order partition depends on where we open our chain. It can be written linearly in one of the following forms. So let's consider, for example, the last one. This is our partition. And our openers again, 2, 1, 6, and 5. So for statistic NSB, we need to move it to the right. So our statistic NSB equals 2. And again, for statistic RLB, this is the minimal element from the right to left. So this counts for our statistic. This is the next minimum, but with respect to definition of statistic RLB, it's not taken into enumeration. So our statistic RLB equal 1. For elements, this should be moved to the right. This should be moved to the right. So 3 elements. And now right to left elements. Here, block starts from the minimal element of the block. Here we have this contributes to RLE. This one again contributes to RLE, and this is the minimal element of a block. This is the minimal element, and this is the single element. So statistic RLE will be equal to for this set partition, and this set partition will be written by term alpha beta squared lambda squared mu cube. So actually, by applying such opening of cyclically ordered partitions and noting that, again, we have complementary statistics, we get again that we have partitions with I blocks and J elements, NSB, NSE. So our coefficients again are given by the product, the same product of 3 Stirling numbers, 2 unsigned Stirling numbers of the first kind and Stirling number of the second kind. So this function with 2 deformed exponentials will have this explicit form. So again, if parameters alpha, beta, lambda, mu will be integer numbers, we again get the integer coefficients here. Everything will be integer.
So how is it different than the one you had before for non-cyclically? This is very
In
similar
form, yeah. In explicit form, it seems to be very similar, but this is changing
the
the
monomial.
parameter itself. If for cases, previous cases, we have this variable and this one, now we have complementary lambda, alpha and lambda.
Interesting. Can you derive one from the other? It's completely independent.
No, I can take, if I'm considering statistics, I can take, let me show, I can take here the table. For example, for combinatorics, obviously I cannot have simultaneously cyclically ordering and uncyclically ordered in the same partition.
So maybe there's some transformation by Jackson we can derive the new case from the old one. Or you have to do it from scratch.
Yes. So the nice feature here, let me show just the generating functions, and I will tell a few more words about nice properties. So this case we already saw these 4 generating functions for 4 set partitions that we already mentioned. But now we take parameters here, our parameters alpha lambda, so we are counting cycle orders. This will be generating function with those parameters. But now applying different values for our parameters, we will obtain generating function with 2 log, 1 log, another 1 log, and exponential function. And this one also appears here, the last one. Corresponds to values of 1, 0, 0, 1. And nice property here is that we have actually one function describes this function, describes also exponential and logarithmic, two functions which are in compositional inverse to each other. And we consider statistics, the statistics also became complementary to each other. We have complementary statistics for compositional inverse of functions. And this property, I'm not sure that it was described in other cases, because as I mentioned, for example, for Q calculus, not each function has compositional inverse, or it's not defined, or it's not found still with nice form. So here we have this nice property. And so yes, we got one generating function for 9 different kinds of set partitions. And again, if we have taken just parameters alpha, beta, lambda, mu, b to be something else not related to set partitions, we still get this nice expansion of any function of such form. And this is all that I would like to present today. Thank you for your attention.
Let's unmute yourself and see. We have 2 minutes for official questions, and after that, people are welcome to stay for unofficial questions. Any questions about? So I have a quick question. So it's really amazing, all this, so many parameters. So what was the motivation? Was it combinatorial, or first you had this?
No, it started as generalization of two-short polynomials, but I was working with Tufik. So Tufik said we need to consider some combinatorics behind it.
Ah, yeah, it's so natural. All this.
Yeah. So no, we got. Yeah, it's the combinatorics appeared. Then we got a recurrence relation.
Mm.
From recurrence relation, I got the vision what it could be, what it's enumerating.
Interesting. And did you try? So you have 4 parameters. So since you have generating functions, be interesting to look at the average and other statistical properties.
Yes, yes, I'm considering it now.
Yeah, that'd be really neat. Yeah, because this ends up former part of the talk. Robert, please stop recording, but people are welcome to stay for a few more minutes. Thank you.